Hello, hello everyone. Okay. Right. So I'll share my screen. So today we are going to talk about the center of mass. So this is assignment 4. Who started assignment 4 for physics? Who's how many? And if you have started, just write how many questions you have done. If you haven't started, just put 0. And chat 0. Alfie. All right, so it seems just only Alfie for now. Okay, so fresh start. So the center of mass. So what is the center of mass? Well, like in mechanics, we often deal with point objects. So we have an object with no size. And the movement of that object, we use Suvat equations to describe the movement of that object. But objects are not necessarily point objects. So some objects can be considered point objects in certain scenarios. So for example, if you are looking at a plane traveling from London to Sydney, I don't know if that's possible. I don't think it's possible. From London to Perth, there's a plane flying from London to Perth, and you look at this tiny dot on the screen as it goes. So the plane is a point object. You don't need to consider that the plane has any size. If you're sitting in the plane, though, or you're pilot and piloting the plane, you can't consider the plane as a point object because, well, because it's not a point object to you. It has dimensions, it has a size, and when you steer the plane, for example, you have to consider its wings, that you don't hit anything, etc. You need to hit the runway at a very precise location. But when you have many objects in a system, or an object consisting of multiple points, you kind of need to just a second, can I switch that off? Hopefully. You view a single object as a collection of objects. So consider this example. It's a video. So this is an object, and the center of mass of that object is labeled with a red dot. And see what happens when we throw this object. Watch again. So the center of mass looks like it's just a ball being thrown up. The white dots move, well, reasonably chaotically. They move in a circle around the red dot, but the red dot behaves as if it was a single object. And that's what we mean. The center of mass moves as if, that's the main thing, the center of mass of a system moves just like a point object of the same mass. The center of mass of a system moves just like a point object of the same mass would. Okay. So for example, you throw this complicated object. And you give it an initial velocity. So if this is the center of mass, let's say this is the center of mass, and you throw it, no matter how it rotates or moves, the center of mass will travel in a parabola. The center of mass will travel in a parabola, and any other point, let's take for example a point somewhere here, it will move like this. But the center of mass will follow exactly the same path as if it was a point object thrown. Does that make sense? Are you on board with everything I've said so far on a scale of 0 to 10, please? 10 being you understand fully what I'm talking about. Lots of 10s, a couple of 12s. Right. Right. Okay. And we have a formula to find the center of mass. So the position of the center of mass is mass 1 multiplied by R1 plus M2 R2 plus etc. plus Mn Rn divided by M1 plus M2 plus etc. plus Mn, where you have this is a system of n objects, of mass M1, M2, etc., Mn. Okay, so how does it look like? Well, if you have 1, 2, 3, 4, 5, 6, and you have an origin, so this is R1, R2, R3, R4, R5, R6. So this is R1, R2, R3, R4, R5, R6. And when you add all of these vectors multiplied by their respective masses and divide by the total mass, you will get a new vector like this. And this vector will be R center of mass. So this would be the center of mass of the system, and the vector drawn to that is the radius vector, the position vector. The origin is an arbitrary point. It doesn't even have to be the origin, or the origin can be chosen randomly. And for if you have only one dimension to consider, this equation becomes much simpler. X center of mass, well, it's not really simpler. It's M1 X1 plus M2 X2 plus etc. plus Mn Xn divided by M1 plus M2 plus etc. plus Mn. So we introduce the x-axis. We choose where the 0 is going to be. So this is 0, this is 2, and this is 5. And so that means x1 is 0, x2 is 2, x3 is 5, and the masses are here. So the position of the center of mass of the system is the mass 1, so 5 times 0, plus 4 times 2, plus 1 times 5, over 5 plus 4 plus 1 gives you 8 plus 5, 13, over 10, 1.3 meters. Okay, so that is 1.3 meters. It's somewhere here. So if you put a pivot here, the system will be balanced. So 1.3 meters. You put a pivot somewhere here, center of mass of the system. And of course, you'll need rods connecting the balls. It's light rods. That's a good question. So Alpha is asking, will there be a webinar next week? Will there be a webinar next week? So we're having 2 weeks off. So next week, yes, webinar, yes. Then we take 2 weeks off, okay? Because I won't be able to do a webinar on the 3rd, definitely. So next week, yes. Right. Does this question make sense to you on a scale of 0 to 10, please? Again, the solution. Okay. Problem 2. Oh, and there's an interesting consequence of that. There's a consequence. Let's say consequence 1. Consequence 1. With no external forces, the center of mass does not move. Well, or moves with a constant velocity. Center of mass remains, well, does not move or moves with constant velocity. And if you think about it, it brings you quite unsettling results. Let's say for example, where should I put it? Okay, example. If you have a boat, and you're standing on the boat. So it's you and the boat. So let's say the center of mass is somewhere here. If you walk to the other end of the boat, the boat would shift to the left slightly. The boat would shift to the left, but you would shift to the right. And the center of mass should stay where it was. The center of mass does not change because there are no external forces. As you walk to the other end of the boat, the boat moves, but center of mass for very large systems like the solar system, is there a point at which we ignore objects as they have negligible effect on the center of mass? Well, yes, we can ignore the asteroids, for example, and some smaller planets. Right. I'm not sure what you mean by zoomed in, Alistair. As you walk to the other end of the boat moves, but center of mass stays still. That's example 1. Now, example 2 is less. So this example is quite satisfying, actually. But the example 2 is going to be quite unsettling. So if you have a rocket in space, a rocket in deep space, and it expels gas. So this is the gas, and this is the rocket. And initially, the center of mass is here. Well, the center of mass is somewhere here because the gas is inside the rocket. Okay, the gas is inside the rocket. So the center of mass of the rocket is somewhere inside the rocket. But now the rocket travels 50 million miles that way. The expelled gas also travels in the opposite direction because it's in deep space. Nothing stops it. Gas rocket. So the center of mass remains where it is. Or in other words, whenever a rocket is launched anywhere, the center of mass remains on the launch pad. Center of mass of rocket remains on the launch pad. Quite unsettling in a way. I don't know, but exciting to think about it. Like, oh yeah, that's true. And example 3. There was an invention of a rocket which doesn't need to expel fuel, which is impossible. The rocket has to expel fuel. So what is center of mass for that for the rocket plus fuel? But I mean, the fuel is part of the rocket. Center of mass of the rocket plus fuel. Okay, of course. I mean, The center of mass of the dry rocket does not. So a rocket with which doesn't expel gas, rocket that doesn't expel gas, fake, of course, because in a with no external forces, you cannot change the position of the center of mass of the system. That's fundamental. That means if you have a rocket that doesn't expel any mass, the center of mass will remain where it is. And there's nothing you can do about it. So the invention looked like this. So it was a semicircular tube. Semicircular tube. There were people inside, so it's a rocket. Space in a space suit, of course. Okay, that's circa beginning of the 20th century invention. And inside the rocket, in this circular, you have water circulating. Water is circulating like this. And the idea was that as the water travels in a curved path, there is centrifugal force pushing on here, and there's no centrifugal force here on the bottom part. So as it travels down, there's no centrifugal force. So here you have centrifugal force, centrifugal force pushing up. There's no centrifugal force here. Centrifugal force here, and this is how the rocket propels itself up. Okay. Can anyone spot the problem with this invention? Or okay, do you understand how this invention is meant to work? Centrifugal force is when you go in a curved path, the liquid is pushing away. Yeah, it's pushing. The liquid will be pushing onto the walls. And because it's not traveling in a curved path here, it's not going to push on the walls. So that centrifugal force is supposed to propel the rocket up. Do you understand how this invention is supposed to work on a scale of 0 to 10? Okay. Right. Alistair, I'd be happy to explain. Like, do you understand centrifugal force? By the way, never mention centrifugal force in school, okay? Never, like this is a no. This word will trigger any physics school teacher. So never use it. We will have an assignment which will mention centrifugal force, but just especially in your mock exams, just like no. This is the banned word. Centrifugal force is complicated, and people study it in second year of uni. And the problem is that a lot of people confuse centrifugal as centripetal force. So whenever you say centrifugal force, your teacher will automatically assume that you have confused centrifugal and centripetal force, and they will not be happy about it. So just avoid using it. Now, centrifugal force. Well, I mean, it's if you have a centrifuge, like clothes in a washing machine, and they spin, you can see that the clothes seem to be pushed towards the edges of the centrifuge. The same way as that clothes, like if I take an object and I spin it, yes, the force that seems to be pulling away. Right, I'm saying seems to be pulling away because it's not exactly what happens. It's much more complicated. We'll cover that in year 13. But this force this is the force that the drivers, like Formula 1 drivers, experience as they go around a curve. They feel as if they're being pushed outside the curve. And the water traveling in a circle will push outwards, and push the rocket up. Does that make more sense? Who was that? Alistair. Alistair, does that make more sense? But won't the rocket push the water back down? Yes, the rocket would push the water back down, true. But if we are talking about the rocket itself, the rocket is being pushed by the water. Now, the problem with this invention is that we have drawn a nice circle here, but we forgot that here the water is also traveling in a circle, like here, around these curves, and it's applying a force in that direction and that direction. So these three forces cancel out. So the water pushes not only here, but also pushes here, and overall the forces cancel out. And yeah, so that's the problem with this invention. And bottom line is, you cannot make something move, or you cannot change the position of the center of mass of a system without external forces. Good. So here we have two identical small masses held 1 meter above the table, are connected by a compressed spring and a short string. So you have a string and a spring. The rope, the string, the short rope, is cut and the masses move in opposite directions. The lower mass hits the table 0.2 seconds later. Find the position of the second mass when this happens. Right. So they are asking us where this mass is going to be, but they're telling us nothing about the way how it moves. They only are telling us how the bottom mass moves. Bottom mass moves. And it moves in a way that it hits the table 0.2 seconds later. So the bottom mass hits the table, so T is 0.2. So where is the second mass? Well, I am assuming it's going to be somewhere here. Somewhere here, but we don't know. And then we remember the position, the center of mass of the system moves as a point object would. So center of mass moves freely under gravity. So even though the one mass goes one way, the other mass goes the other way, the center of mass will behave as if it was a free falling object. It would just fall down. If there was a red dot that we could draw, the red dot would just fall down. And we can use that. the center of mass, so we use a SUVAT for the center of mass. So the displacement, well, we don't know the displacement. That's what we're looking for. U is 0. V is we don't know. Acceleration is G. Well, let's like 10. Acceleration is 10. I'm saying down is positive. Oh, that doesn't make any sense. I'm going to say that the x-axis is upwards. This is 0. This is 1. Okay. This is 0. This is 1. And this is what we are looking for. So x2. X2 is what we are looking for, where the mass is. So initial velocity is 0. Acceleration is -10. And t is 0.2. V is we don't really know. Okay. And we can see that the center of the displacement, well, the position of the center of mass, is equal to the initial position of the center of mass plus ut plus 1/2 at squared. So the position of the center of mass, initial position of the center of mass is 1 meter, plus initial velocity is 0, minus 1/2 multiplied by 10 multiplied by t squared, 0.2 squared. So position of the center of mass of the system is going to be 1 minus, so that's 5 times 1, so 0.2. 0.8. So the center of mass is going to be here. Center of mass at 0.8. So where's the second ball? (1.6). Brilliant. X2 is 1.6 meters. I think I've overcomplicated this. Let's do it again, but just in a simpler way. In 0.2 seconds, center of mass falls by S equals 1/2 gt squared, which is 5 times 0.2 squared, which is 0.2 meters. So center of mass is height 0.8 meters. So second ball is h2 equals 1.6 meters. That kind of makes more sense. I think this is just overcomplicating things. Do you understand this, guys? On a scale of 1 to 10, please. Good. Good. Find the volume of a square pyramid of base length base length 4 and height 7 by slicing it into thin square slabs. So this is a math question, but it is related to physics. So find the volume of a square pyramid. So we have a square pyramid. And I'm sure you all know that the volume of the pyramid is 1/3 area of the base times height, just like a cone. But we are not allowed to use this formula. But let's just check what we are expected to find. So the area of the base length is 4. So 16, so 1/3 times 16 times height is 7. 28, 112 divided by 3. 112 divided by 3. Is that it? Doesn't seem like 112 is divisible by 7. So 42 and 7, yeah, 112. 112 over 3. This is the volume that we are looking for. So this is how to check. We're going to check ourselves. What we do is we put the pyramid sideways. We put the pyramid sideways and draw some axes. I'm going to put the pyramid like this. Okay. So this is 7. This is 0. And this is X. This is Y. So if the base length is 4, so this is going to be 2. 2. And this is, of course, minus 2. So this is a cross section of the pyramid put sideways. Okay. Now the pyramid, we can slice the pyramid into square slabs. That means we can cut the pyramid like this, and we can assume that the pyramid is made of cuboids. So just like in preschool, you probably had something like this. Put a square slab on another square slab on another square slab, and you got a pyramid. Okay. I don't know if you played with toys like this. Well, not exactly like this, but I hope you're getting the point. So if you take a square slab like this, put another square slab, and then another square slab, etc. So you can build a pyramid. If you take really, really thin slabs, you kind of make a perfectly smooth pyramid. So the pyramid is made of square slabs like this. You can assume. The width of the slab is delta x. The height of the slab is y. And this is because this is a straight line, we can say y is equal to 2 over 7x. Yeah, y equals 2 over 7x. So the width of the pyramid is equal to 2y, of the slab, 2y. And the volume of that small bit, delta V, is equal to the area, so it's 2y squared multiplied by delta x. All right. So the volume, if it's the sum of volumes, is a sum of delta v's of this is delta vi. So the total volume is the sum. Is approximately the sum, sorry, because it's not exact. We are approximating. It's the sum of 2y squared delta x delta yi. It's the width of the ith slab, and we replace y with 2 over 7 times x. So it's the sum of 4/7 x squared delta x. And now the magic bit. The volume is equal to the limit of this Riemann sum, 4/7 x squared delta x, as delta x tends to 0. And when the limiting value, when we have a Riemann sum, the limiting value is the integral of 4/7 x squared dx. So delta x becomes dx. Right. And then you can put the limits as 0 and 7, because that's the limit for x, 0 and 7. Then you just integrate it. So it's 16/49. The integral of x squared is x cubed over 3. So you put 7 and 0, so 7. So 16 multiplied by 7 cubed divided by 49 times 3. So 7 cubed and 49 cancels. So it's 16 times 7 over 3, which is 112 over 3. Ta-da. This is the volume of the pyramid. Okay. Right. Honestly, I'd like an honest vote. How well do you understand what we have done here on a scale of 1 to 10 again? Could you ask me if you don't fully understand, do you have a question that you would like to ask? Can you show how to actually integrate from the start of the blue? Oh, of course. Right. So you open the brackets. So it's 16/49 x squared dx. Because the integral is linear, you're allowed to take 16 over 49, 16 on 49 out, and you're left with the integral of x squared dx, 7, 0. And we know that the integral of x squared is x cubed over 3, so 16/49 is x cubed over 3, and the limits are 0 and 7. So you plug in 7 first, so 16/49. You put 7 cubed over 3. Then you put minus and you plug in 0, so 0 cubed over 3. And that makes 112 over 3. Y equals 2 over 7x. I needed the equation of this. I found the equation of this line. Yes, the equation of this line. And this gradient of this line is 2/7. So this is y equals mx plus c. And I worked out that m is 2/7 and c is 0 because it goes through the origin. So this line is y equals 2 over 7 over x. Okay. The summation part. The pyramid consists of square slabs of width delta x. Each slab has a volume. the volume of this slab, so if you look at this slab separately, you can take that this is delta x, that's the width, this is 2y, and this is 2y. So the volume of this slab is delta V is equal to delta, because it's part of the whole pyramid, is 2y squared multiplied by delta x. Now you have multiple slabs here, not just one. You have many slabs. And what I'm saying next is I'm saying that the volume of the pyramid is approximately the sum of all the slabs, of the volume of each slab. Well, we can take the ith slab. So delta V, this is the ith slab. Okay. And each slab has the same delta X, but it has a different Y, different size. So we say it's the sum of 2yi squared delta X, which is the sum of 4/7 x squared delta X. Does that make it more clear, Arman? Okay. Now, find the position of the center of mass of the pyramid, of the above pyramid. Density of the pyramid is rho. So we have the same pyramid. So this is 2, this is 7, this is x, this is y. The slab. So we take a slab here. Now we not only need the volume of this slab, so delta x. So consider the ith slab. So width delta x, length is 2y. Okay, so 2y is the length of the slab. So the volume is delta Vi is equal to 4/7 x squared multiplied by delta x. And the mass is volume times density. It's density times volume. So it's density times 4/7 x squared delta x. Mass of the slab. And the center of mass is equal to so the mass of each slab, so the sum of mi multiplied by xi divided by the sum of the masses. Okay. the total mass. Now we could use this to find the total mass. Just integrate that, but that doesn't really make sense because we already know the volume, the total volume. Total volume is 112 over 3. So total mass is 112 over 3 rho. So instead of here, the total mass, which is the sum of all the masses, is this. Sum of mi(xi) divided by just 112 over 3 rho. Is it making sense so far? Is anything here not clear to you guys? Just let me know. Okay. Now we need to focus on this bit. We need to focus on the sum of, because this is all this is easy. So we need to find sum of mi(xi). Well, the mass we know it's rho. It's the sum of rho delta vi multiplied by xi. So it's the sum of rho multiplied by 4/7 x squared delta x multiplied by x. So we can simplify that as sum of 16 over 49 rho multiplied by x cubed delta x. All right. And so we need the limit as delta x tends to 0 of this sum 16 over 49 rho x cubed delta x is the integral of 16 over 49 rho x cubed dx now from 0 to 7. So 16 over 49 rho integral of x cubed dx, so which is 16 on 49 rho integral of x to the power 4 over 4 between limits 0 and 7, and it's 16 on 49 rho 7 to the power 4 divided by 4. So 7 to the power 4, that's 49. 16 divided by 4 is 4. So 49 times 4 is 196. 196 rho. So we put that into here. 196 divided by 112 third rho cancel out. Well, I'm going to use a calculator for this one. 196 divided by 112 times 3, 5.25. 5.25 meters. That's the center of mass. And does it make sense? Well, if you look at the graph? Yes, it does, 5.25. The center of mass is here, 5.25. So it's closer to the base of the pyramid, which it should be. So all we are doing here is we are saying, look, the pyramid consists of slabs. And each slab has its mass, M1, M2, M3, M4. And each slab has its coordinate, x1, x2, x3, x4, etc. And all we're doing is we're saying, look, the center of mass is m1 x1 plus m2 x2 plus etc. plus mn xn divided by the total mass, m1 plus m2 plus m3 plus etc. plus mn. It just happens to be that the sum of the masses is the integral of m times of x. Well, it's the sum. It's the sum of mi xi divided by the sum of mi. And it turns out that this is the integral of what? 1649 rho x cubed dx. And this is the integral of 1649 rho x squared dx. Interestingly. And like overall, simply put, I would imagine. I can't guarantee. I can't tell you the answer to that question. Okay. Okay. I don't have the answer to this question. I would. Yeah, it depends on the size of the base, of course. But then again, what I would do if I were you, I would take a pyramid with base A and height h and work out in terms of A and h and see what it gives you. Okay, let it be an exciting exercise for you. So repeat this. So what you will need is you will have this. The integration between will, so this is A. Well, this is, let this be A. So the base is 2A. The base of the pyramid is 2A. So this is A, this is minus A. So this is okay. Ooh. A is 2A, 2A. The height is h. H. So this would be h. This is A. So the line y equals A over h x. So you have the integral of A over h x squared dx between limit 0 and h. So it gives you something. So it's going to be a squared x squared, h squared divided by h squared. Oh, interesting. Just going to be a squared somehow. Doesn't make any sense. Oh, because it's going to be a cubed over 3. So it's going to be a squared h over 3. That's the volume of the pyramid, and then you have well, work it out. Okay, I'm not gonna to be continued. To be continued by you, of course. Next, and I love this one. I think one of the problems in the assignment is you will need to take this semisphere. So you have a semisphere, and one of the problems in the assignment, you need to find the center of mass of the semisphere. You do it in exactly the same way as the pyramid. So you cut it into cylindrical slabs now. So each slab is a cylinder. So like this. Each slab is a cylinder of width delta x. And so you have width delta x. Y, you need the equation for y. Depends on how you want to do it. I would do it the other way around. So perhaps do it like this. Right, then y is equal to square root of radius squared minus x squared. Right, then you have a slab here. So delta x, the radius is r squared minus x squared. So volume is pi r squared multiplied by delta x. So volume is pi r squared minus x squared dx. And then mass is going to be density pi r squared minus x squared dx. Delta x, and then you do the sum of mi xi divided by sum of mi, and you get something. And it turns out that this point, the center of mass for a semisphere, is 3/8 of r away from the base. Yeah, center of mass of a semisphere or a hemisphere, and it tells you yeah, 3/8 r from the bottom. 3/8 r. So for a hemisphere is 3/8 of the radius. 3/8 of the radius. That's the set position of the center of mass. I leave this to you. I don't fully remember whether it's an exercise, whether it's an example or an actual exercise, which you need to do, but you need to prove this result. Okay. But now we have two objects. We have this ball of mass m, and we have this hemisphere. What is the maximum mass that can be attached to the top of the light pole so the system would not topple over on a flat surface? So why would it topple over? Well, let's try to topple it over and see what happens. So you have a flat surface, and you have this hemisphere, and the center of mass of the hemisphere is here. Well, let's draw it a little bit lower here. And then you have another mass here. Mass is here. Now, you can see that the center of mass is here, the center of mass is here. So the center of mass of the whole system should be somewhere in between. Now, if I draw it properly, this point should land at the point of contact. Point of contact. So like this. Contact. So going back to Vin, it's a volume of the cylinder. It's a cylinder, not a sphere. It's a slice of the sphere, and it's a cylinder. Okay, it's the area of the slice section. Yes. So here we have a point of contact is here. There's mass is here, and the big mass, the mass, the whole thing is here. Is the mass of the big thing is here. So where should the center of mass of this two-body system be in order for it to not to topple over? You can use your voice. I haven't heard you.
Would it be at the point between the sphere and the rod?
So along the red dotted line or the blue dotted line?
Would be like in the sphere.
If it's in the sphere, yes. If the center of mass is here, it will not topple over. It will bounce back to the original position. And if it's if the center of mass is here, for example, then it will topple over. So the center of mass of the system must be kept within this line. So the extreme position is here. The extreme position of the center of mass. Center of mass. So the extreme position. Of center of mass. And I've prepared a nice video for you. So Here you go. So here you see a hemisphere made of concrete. I think he said it was like 2 or 3 tons of concrete. And there's a pole, and he's going to attach a mass to the end of that pole and then see if it topples over.
We can't hear any sound.
Sorry?
We can't hear any sound.
Oh, well, that's you don't need any sound.
Okay.
I could share the audio. Yeah, that's the thing. So you can see the concrete slab, and he's bouncing on it, and it's not toppling over. There's a smaller version. So this is possible because when he's attaching himself to the slab, so because when he's attaching himself to the slab, and here he is, his body has the center of mass around about here, and the sphere has the center of mass here, which is 3/8 from the edge, and the center of mass of the person and hemisphere system is around about here. So when you topple it over, this is the point of contact. The point of contact is directly here. So when you lean it, it pushes it back. So force of gravity pushes it back, creates a anti-clockwise moment. So he returns to the original position. Yes, it does look quite fun. At points, it looked a bit dangerous when he was doing it inside, when he was doing the big one inside the barn. So yeah, look it up. I just accidentally the video came up in recommendations, which I'm so it's Colin Furs. Anyways. So let's do the maths. So what we have, I'm gonna move this to the right. So what we have is a slab, is not a slab, a hemisphere, sorry. Hemisphere, and the mass is here, which is 20 centimeters, 20 centimeters. We're gonna put this as 0. We're gonna put this as 0, and the x-axis is going to go through here. This is x-axis, this is 0. The position of this center, this mass, obviously x2 is 20 centimeters, and x1 is minus 3/8 times 10 centimeters. So 30 over 8 centimeters. We just need to find the center of mass. Center of mass is equal to m1 x1 plus m2 x2 divided by m1 plus m2. So it's m1 is 3 kilograms, and the position of the center of mass is minus 30 over 8 plus m, which is unknown, multiplied by x2, which is 20 centimeters, divided by m1 plus m2, which is m plus, so 3 plus m. And the position of the center of mass must be less than must be less than 0. Otherwise, it will topple over. So the center of mass must be to the left of this. But they're asking for the maximum, so the critical value is equal to 0. And all we need is -3 times, -3 times 30 over 8 plus m times 20 must equal to 0. So m is equal to 3 times 30 divided by 8 times 20, 8 times 20, that's 9 over 16, 9 over 16 kilograms. So about 6 times less for 20 centimeters. The mass is 6 times less than the mass of the hemisphere, which is 9/16 kilograms. Okay, does this question make sense? On a scale of 1 to 10, please. Okay. Right. So problem 6 is about statics. It's not exactly about the center of mass. 7 is find the center of mass of a quarter of a uniform cylinder. We won't have time to do this today, but what it is we have, if we have a cylinder like this, and we cut it into four pieces like this, we get a slice that is cylindrical, is like this. So yes, we need to find the position of the center of mass of this one. And then we find the 3/4 of a cylinder. So it's just 3 identical cylinders. Three of those you take, and then you find the center of mass of this system. It's going to be somewhere here, center of mass. But maybe we'll do this next week because we have some time. So what is this? A light rope of length 4 meters has a 100-kilogram mass hanging from the middle. The central part of the rope is displaced by 10 centimeters. Find the tension in the rope. Okay. Now, when we hang a mass in the middle of the rope will always be displaced. It's not possible for it not to be displaced, because if it is, let's say a rope is perfectly straight, you have tension, 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 and you have mg. And mg is not compensated, is not balanced with anything. So that situation is not possible. Okay, so and that also shows that no rope can be taut so that it's perfectly straight. The rope will always have a bend in the middle. It's impossible to make a rope perfectly straight. Because once, as I shown before, that means the tensions are perfectly horizontal and the force mg will not be balanced. When it's slack though, when it bends, sorry, there's mg, and there's the tension this way and tension this way. Tension and tension, and this is mg. And this is all you need, because we know mg, which is 100, g, which is 1,000 newtons. Let's use, like, for simplicity, just use g is 10. Of course, in A levels, don't use g is 10. 10 centimeters. So we need this angle, theta, and we can split the t into components. Split the t into components like this. Similar way here. So this is t cos theta. This is t cos theta, and this is t sine theta and t sine theta. The theta can be found from, well, from here we can write that mg is equal to 2t sine theta, and t cos theta is equal to t cos theta, but yeah, that's kind of obvious. Then this is 4 meters, so this means that this is 2 meters. So it's the angle theta, the sine of the sine theta is 0.1 divided by 2 meters. Now, is it sine or tan? Well, technically it's tan. It's tan theta. But for small angles, you can use that tan is equal to sine. Tan theta is approximately sine theta. So tan theta. So sine theta is approximately equal to tan theta, which is, this is 1 over 20. So 1 over 20. So you plug that in here. So it's 1,000 equals 2 multiplied by t multiplied by 1 over 20. So that cancels. It's 10. So 10,000. Tension is 10,000 newtons. And the lower, the smaller the amount of slack, the higher the tension. So whenever you see a wire, a stretched wire, something hanging on it, the tension in that wire is many times bigger than the weight of the object. In this case, it's 10 times bigger. And the smaller the vertical movement when you hang something, the higher the tension. So if you have a really big tension, you might not even notice that it moves slightly down when you hang something from it. Right. I think this is all what we have time for today. And yes, thank you for your attention. You will have we'll do another webinar this year, and then we'll have a 2-week break for Christmas. Okay. See you all next week. All right. See you.